Assalamu alaikum. In this lecture, we will learn segmented memory model, segment registers and offset registers. The concept of segmented memory model is to divide the RAM or memory or area where we store data into pieces or blocks or segments. Why segmented memory model? Segmented memory model helps us to increase the compatibility and the memory. How? The compatibility means the programs developed on old processors should run on new processors. For example, if I develop a program on 16-bit processor, this program should run on 32 bits or on 64-bit processors. The increase in memory means with the increase in the capacity and capability of the processors, the memory of the registers and the buses is also increasing. For example, the address bus size has been increased from 16-bit to 48-bit in 64-bit processor. Here I will explain what if we use the linear memory model. We know that we need buses to communicate between processors and memory. Here I would draw a scenario of address bus and data bus to explain a little bit about the communication between processor and memory. Two common scenarios or operations or the control signals from processor to memory are read and write. If the processor wants to read from a specific location of a memory, then the processor would place address on the address bus. Memory would get that address and simply reads the data from that location and put the data back to data bus. Processor would receive data from data bus which was required. In case of write, processor would provide the address as well as the data to the memory to be written on that specific address. Memory would get the location from address bus and would get data from the data bus and simply would write the data on that specific location as specified in the address bus. So we get the idea here that the address or location of memory is being identified through the address bus from the processor. The address bus here is of size 16-bit. So the maximum location or maximum address the processor can access from the memory is that all the 16 bits would be set to 1. And if I describe this in the form of hexadecimal, then we know that 1 hexadigit is equivalent to 4 binary digits. F means 4 1. So FFFF means the maximum location or maximum address of the memory to be accessed via address bus by the processor. And the minimum location can be all 16 bits 0 or 40 in case of hexadigits? Here, if I attach an extra memory here and increase the size of the available memory, if I explain it with the help of a scenario in which we attach an extra RAM in our system, this is similar to attaching an extra RAM in our system. But can we access this extra memory now? The answer is no, as the maximum location can be accessed is all 16 bits of the address bus set to 1. We cannot access the location of the memory after this address due to the limitation of the size. And the memory model is the linear memory model. No hierarchy or segments are given. Here the maximum memory locations are described as 2 raised to power 16, which is 65536, which leads to 64K. And 64K means 64 into 1024. So the maximum capacity of the memory is 64K, which is 64 into 1024. This is the disadvantage of linear memory model. We cannot access the memory attached additionally here. This additional memory would be wasted. So if I increase the memory from 64K to 1 MB, this cannot be accessed based on the linear memory model. This was the disadvantage of the linear memory model. Now we will move towards the segmented memory model. And the first step of the segmented memory model is to understand what would be the segments of the segmented memory model, how the blocks or the regions or the segments of the memory would be decided, how the sizes of the blocks would be decided. First of all, we will understand this. In scenario of segmented memory model, whenever a program is loaded in the main memory or RAM, the program is divided into 4 segments. First one is the code segment, which would contain the instructions of the program. Second would be the data segment, which would contain the variables or arrays being declared in our program. Second would be the stack segment, which would contain the temporary variables or temporary memory allocations of our program. Fourth one would be the extra segment. And extra segment would contain the data of the program related to video memory. We know that at a time multiple programs can be loaded into main memory or RAM. So each program, whenever loaded into memory, would be divided into 4 segments. Each program has its own 4 segments into the memory. Here, it is not necessary that all of these segments should be aligned linearly in the memory. They can be placed apart. For example, we can say that the segments created in the memory P1 are of P1, program P1. Similarly, there can be a program P2 loaded in the memory, and the segments of P2 are code segments, then stack segment, data segment of P2, and then extra segment of P2. So multiple programs can be loaded into the memory at a time, each being divided into the 4 segments. So how to keep tracks of the segments? For this purpose, the processor has some special registers. 4 segment means the processor has the 4 special purpose registers to keep the track of the 4 segments of the program currently being executed on the processor. First segment register is the code segment register. Suppose we say that currently P1 is being executed on the processor, so the code segment register would contain the address or the starting location of the code segment in the memory of P1, as P1 is being currently executed on processor. We know at a time only one process can execute on a processor. Second special purpose register is the data segment register, which would be pointing towards the starting location of the data segment of P1. Third is the stack segment register SSR, which contains the starting address of the stack in the memory of P1. Fourth one is the extra segment register. Extra segment register would contain the address or the starting location of the extra segment of P1 in the memory. Similarly, if the P1 stops its execution and the P2 would be loaded into the processor to execute, then all of these references being removed and the segment registers would start pointing towards the segments or the starting address of the segments of the new process being executed on the processor. So the segment registers of the processors keep track of the segments or the starting location of the segments in the memory of the process which is currently being executed on the processor. Here is the scenario of the segment registers redrawn, and the segment registers keeping addresses of the starting locations of the segments of the process currently being executed in the processor. To increase the capacity of the memory or to create a hierarchical view of the memory, the processor needs the offset registers as well. But before explaining about the offset registers and how offset should be decided, again I am explaining here about the segment registers and how segment registers are pointing towards the segments of the process being executed on the processor. Here in the scenario of the memory, 3 processes are being loaded in the memory. Each process has been divided into the 4 segments and each segment has its own starting address in the memory. Whenever a process is being loaded into the processor, then its starting addresses would automatically be loaded into the segment register. The starting addresses of the segments of the process being executed on the processor being loaded into the segment registers. Each segment now contains 64K in the memory. In case of linear memory model, whole memory block was of 64K. But now here in case of segments, each segment is of now 64K. Total program is comprised of 4 segments, so by adding 64K 4 times, we get total of 256 KB for each program. Space of 256 KB for each program in the memory comprising of 4 chunks or 4 segments of 64K each. Now here we can see the code segment register contains the address 10, which is pointing towards the starting address of code segment in the memory. And we have explained that each segment is of now 64K in case of segmented memory. Each segment again would have its own addresses starting from 0 to, if I write in hexadecimal, 00002 F F F F. This was the case in linear memory model with the whole memory block, but now this is the scenario with one segment in the segmented memory model. Again, if I draw the addresses of data segment as well in hexadecimal digits, location starts from 00002 FFFF, as we know that one segment is now of 64K. So by hierarchical addressing, our addressing capacity has increased. Our memory utilization has also been increased. But now the question is, how can we access the inner addresses of the segments? We know that we can access the starting location of the segment by utilizing the segment registers. For inner addresses, we need the offset registers. Here, the code segment register is pointing towards the starting location of the code segment in the memory, and the value in IP would be pointing towards the offset value inside the segment, or the address inside the segment. We know that in code segment we have the instructions. Let's suppose the first instruction is move AX, 2, and the second instruction is move BX, 2, and we know IP decides which instruction to be executed on the processor, or the address in IP decides that which instruction to be fetched to be executed in the processor. So here we can say that the code segment register is pointing towards the starting value of the code segment of the process which is currently being executed on the processor, and its corresponding offset register is stating the location from where the instruction to be fetched from the code segment. Similarly, the data segment register is pointing towards the starting location of data segment in the memory, and its corresponding offset register, which is BP, is pointing towards the offset inside the segment. So each segment itself is now 64 KB, starting addresses from 0 to FFFF, which has resulted into the increase in the memory capacity. Each segment register has its own offset register. For code segment register, the offset register is IP or PC. IP stands for instruction pointer and PC stands for program counter. And data segment registers offset register is BP. BP stands for base pointer. Similarly, for stack segment register, the offset register is stack pointer. denoted as SP. And for extra segment register, the offset register is SI or DI. SI stands for source index and DI stands for destination index. And the purpose of offset registers is also to contain the address. Which address? The address which describes the location inside the segment from where we have to extract the data. Both segment registers and the offset registers are of 16 bits each. When computing the address, we get the 16 bits from the segment registers and the 16 bit from the offset registers. But we have to compact this address into 20 bits as we are having 20-bit address bus in our scenario. So how we would translate both of these 16 chunks into the 20-bit address, this we would cover in the next lecture of translation of logical address into the physical address. The notation to write the segment registers and offset registers should always be something like that. We should write the segment first and then colon and then write the offset register. Offset cannot be written before the segment. As I put the crosshair, this differentiation has been fixed by the developers of the registers. Here I am illustrating the scenario where we have to compute the address of 20-bit, as the address bus between the processor and memory is of 20 bits in size. But the architecture we are following have the register's capacity in the 16-bit, which means the 16 bits address would be saved in the segment register, and similarly the offset register's address would also be of 16-bit, and we have to compute the 20-bit address. The solution of computing the 20-bit address to be placed on the address bus of 20 bits in size is to take the 16 bits from the segment registers and the 4 bits from the offset register. For this purpose, we have to apply the rules of logical to physical address translation, which we will cover in the next lecture. Thank you very much. Best of luck.